Hello, and thank you for joining HOCKLE Consulting's presentation for the reconstruction of Shaw Lane and Shaw Power Plant renovation done for Michigan State University. HOCKLE was founded in 2020 as an engineering startup based in East Lansing. To tell you more about ourselves, our specialties involve architectural design, construction management, hydrological engineering services, and transportation design. Because we are presenting this presentation virtually, our team wanted you to be able to put a face to our voices. My name is Alexis Edge, and I am the team's project manager. We also have Alex Caprios, who you will hear from later, our structural engineer, Evan Offerly, our hydrology engineer, Eric Hecken, our pavements engineer, and Josh Cole, our transportation engineer. The scope of this project stems from goals directly outlined in MSU's 2020 Master Plan. First, a new STEM learning facility was desired in the location of the old Shaw Power Plant. This building was to be renovated, but the HOCKLE team also decided to expand the building's footprint. This would allow for more classroom, laboratory, and office spaces. This facility would become ultimately a central hub on campus, so coupled with the construction changes in the area, a segment of Shaw Lane would need to be repaired, and also the traffic would need to be rerouted differently in that area. Here we can see an aerial view of the proposed site area. The segment that is going to be repaired is perpendicular to Chestnut Road and Red Cedar Road. In this segment of the map, we focus in on the decommissioned Shaw Lane Power Plant. This will be the location of the proposed STEM building. At HOCKLE, we use several interdisciplinary fields to accomplish the scope of projects we take on. Each further addresses field-specific goals. We do not have an environmental engineer on our team, but all environmental information has been contracted to other firms that MSU has hired. Nonetheless, we still work to incorporate environmental sustainability in all aspects of our work. Next, I would like to discuss some of the discipline-specific areas we focused on. Our objective in the hydrology area was to create a stormwater management system that could accommodate the new academic STEM building. Adjacent to the site area, there's also the Red Cedar River, so we wanted to minimize the impacts to that concerning the effluent leaving the piping networks. We also wanted to determine the most cost-effective way to do this and abide by Ingham County Drain Commissioner regulations. In order to combat adverse effects to the Red Cedar River, the HOCKLE team designed their stormwater management system to actually decrease the flow rate into the river. We also implemented several other strategies to help improve water quality of the runoff entering the stormwater management system, which we will discuss later. Concerning the structural objectives of this project, we needed to take into consideration the different types of loads that the building would encounter. This could be live loads from the increase in students and faculty due to the different resources and opportunities the new building will offer, dead loads from fixed objects like machinery and lab equipment, different loads from different types of rooms, and also weather loads like snow and wind. The development of the academic building has many interdisciplinary considerations with hydrology due to the fact of the Red Cedar River water reservoir. So with that, there are economic considerations, safety, sustainability, and environmental consciousness to make sure that the building is harmonious with the surrounding area. Our transportation objectives involve being able to provide a reasonable level of service on Shaw Lane. We also wanted to maintain parking accessibility. Because North Shaw Lane is going to be completely closed and only accessible to pedestrians, all of the traffic will be rerouted through South Shaw Lane. Level of service is based on a grading scale of A through F, and they have different speed designations based on the type of road. Examples include freeways and one-way streets. These transportation considerations are important because the current design only accounts for traffic for a certain level of service that may not accommodate future activity. Our pavement objectives have many interdisciplinary considerations with transportation engineering. First, we want our pavement to be able to withstand traffic movement without deforming or cracking. Also, by Michigan Department of Transportation standards, it must have a durability of at least 20 years. We also want our alternative to be cost effective. Our pavement considerations are important for many of the same reasons as our transportation engineering considerations. Regardless, pavement must be able to accommodate future activity. The reworking of North Shaw Lane is a significant financial investment for the university, and the pavement design must account for that certain level of service that will be experienced. Moving forward, we will now hear from each of our consultants to describe the design process of each discipline.
Hello, my name is Evan Offerly, and I am the lead hydrology engineer here at HOCKLE. The new proposed academic building on Shaw Lane will require an entirely new stormwater management system that not only manages and reduces the amount of runoff from the project site, but also increases the water quality. The solutions to these problems involve the installation of a green roof on the new building, the creation of 6 new rain gardens, and the construction of a new underground storage tank. The implementation of these technologies will not only help meet, but they will help exceed laws and regulations set forth by the Ingham County Drain Commissioner. These regulations involve limiting the amount of runoff leaving the project site to 0.15 CFS per acre. This equates to roughly about 2.3 CFS for the entire project site. The Commissioner also requires that a detention tank must be able to accommodate a 100-year, 24-hour storm while still meeting the maximum 0.15 CFS per acre of runoff constraint. To account for the instance where there might be consecutive storm events, the system must also be able to drain itself within 24 to 48 hours. After talking with the structural engineer Alex, we decided to implement a green roof. The green roof would act as a retainer of water that would slowly release it, ultimately increasing water quality and decreasing runoff. This green roof is designed to be 300 square feet in size and 3 inches thick. The building structure was designed to be able to support both the live and dead loads of this design. The green roof would consist of heavier trees and bushes towards the outside where there is more support, and grasses, herbs, and succulents more towards the middle. This is what a typical rain garden would look like. Rain gardens slow down the amount of runoff entering the system, as well as providing natural filtration to help increase water quality before it enters the system. These gardens are strategically placed in areas such as the parking lot that have high runoff coefficients and are positioned over inlets to maximize their effectiveness. Having these gardens located in the parking lot will also increase pavement longevity by providing natural coverage. Due to surface level space constraints, an underground detention tank was chosen as opposed to an above-ground detention basin. This tank is designed to keep the outflow to the existing stormwater system below 0.15 CFS and be able to manage a 100-year 24-hour storm, as well as drain within 48 hours during a 2-year 24-hour storm. This underground tank can be located below pavement, therefore the placement of this vault can be adjusted to project needs. The preferred placement would be in an area easily accessible by trucks to allow for easier maintenance and installation. The outflow of the storage tank is designed so that the tank will be able to retain the first half-inch of rainfall, as well as accommodate the tie-in to the existing system. This graph shows the inflow and outflow of water to and from the storage tank during a 100-year 24-hour storm. As you can see, the outflow never exceeds the maximum 2.3 CFS, even while the inflow is significantly higher. This first graph shows that during a 100-year 24-hour storm event, the depth of water peaks a little above 4 feet. The second graph shows the drainage of the tank during a 2-year 24-hour storm event. As you can see, the tank is almost completely drained after 35 hours, meaning that it fits the drainage requirement of under 48 hours. The design was an iterative process consisting of adjusting pipe slopes and sizes to accommodate the tie-in, storage tank height, and velocity requirements at the same time as remaining below the frost level while still minimizing excavation and pipe length to limit project costs. The storage tank design required adjusting the tank area, outlet area, and runoff coefficients of the catchments to keep the outflow into the existing stormwater system below 2.3 CFS at the same time as being able to store the first flush and 100-year storms peak depth, as well as meeting size and elevation requirements for the tie-in. The tank was also required to eliminate its contents from a 2-year 24-hour event within 24 to 48 hours in case of concurrent large storm events. This is an overview of the stormwater management system consisting of low-impact features and as well as the piping network. The low-impact features are seen in green and the pipe network can be seen in orange. The underground storage tank and the tie into the existing system is seen in the top right corner. Cost estimations were calculated using the 2019 weighted average item price report from MDOT. As you can see, the majority of costs come from grading and excavation. The low-impact features will cost roughly $316,000 altogether, but will provide necessary reductions in runoff and improvements to water quality. The final cost estimates for the installation, excavation, materials, operation and maintenance, inspection, grading, and engineering design of this necessary stormwater management system is roughly $2,052,000. This preliminary schedule was developed using construction time estimates provided by MDOT. It is estimated that from start to finish, the stormwater management system will take roughly 88 days to complete. However, some of these activities can be completed in tandem, overall decreasing the construction time.
Hello, my name is Alex Kipros and I was in charge of the structural engineering part of this project. The role of the structural engineering portion was the development of architectural and structural drawings leading to the construction of a new STEM educational facility. These drawings were developed according to the restraints detailed by the lead architect in conjunction to the governing codes and regulations. These drawings and an understanding of the loads and governing load combinations led to the development of member sizes that allowed for a cost estimation of the total building. The aforementioned restraints put out by the lead architect and MSU itself require the HOCKLE structural design team to put together drawings with adherence to a certain quantity and square footage of various rooms that will lead to an ultimate utilization of 75% of the building's entire space. This 4-story building cannot exceed 65 feet in above ground height, nor can it be constructed utilizing wood as its primary supporting material. In addition to this, the new facility must be designed utilizing the footprint laid out by the lead architect. The constraints laid out in the owner's requirements were not only met but far surpassed, as you can see by the table in the bottom right. This design was of course developed in conjunction with the specifications laid out in the 2015 Michigan Building Code, the 2015 Michigan Plumbing Code, the 2010 ADA standards, and the International Building Code. The next handful of slides depict the architectural drawings developed by the HOCKLE design team. As the team developed these drawings, they had an understanding of the many students and faculty that would be going through this building and therefore streamlined the first and second floor to allow quick movement. However, the team wanted to emphasize collaboration between students and faculty, which you can see through the use of unwalled study areas, especially on the 3rd and 4th floor. The basement was primarily designated for technicians and storage. As the team moved forward toward designing the frame for this structure, we had some obvious considerations. Steel was the clear choice for this project, not only because of its versatility, but also due to its availability in the East Lansing area. There are 3 steel mills in a 63-mile radius of the job site. Brace and pin connections were chosen for this structure because of its ability to minimize internal forces, which allow for less material and less overall cost, unlike moment connections. The design team decided to go with a pitched roof for this project because it will allow for the active reduction of East Lansing's snow load. The steel frame was determined understanding the footprint's dimensions laid out by the lead architect and by keeping a sustainable range of 20 to 30 feet in mind. Multiple viewpoints of the steel framing is shown in the following slides. Utilizing ASCE7, the team was able to fully determine the loads that will be acting on this structure. The team decided to apply these loads through the LRFD design combinations, which will eventually allow for objective calculations to determine appropriate member sizes as opposed to ASD specifications. Once the loads and load combinations were determined, they were appropriately applied to a 3D model of the structure within the SAP 2000 software. Due to the symmetry between buildings, only the analysis of the southernmost building was necessary. The SAP software took the applied loads with the load combinations and calculated the shear forces, axial forces, and bending moment for each member according to each load combination. The team determined that the structure would receive the most load for the second load combination. The team then isolated 4 frames, 2 interior and exterior frames, which are also separated by width and length to understand the members with the maximum forces for different criteria. The design and sizing of the previously mentioned members was then used to understand the member sizes for the entire structure. As shown in the above table, the axial loads applied upon column 565, which is the ultimately loaded basement column, require the use of a W14 by 109 member, as specified by the LRFD design specifications. This column size was then used for all columns in the basement and first floor of the structure. Similarly, column 567 had the ultimate axial load for columns on the second floor. Therefore, all columns on the second, third, and fourth floor will use W12 by 45 as their member sizes. The same process was used for the remaining members and the entire structure, by which beams were differentiated by interior and exterior, trusses were specified by tension and compression, and all bracing members were the same. As mentioned earlier, the LRFD design specification allows for objective means to determine the safety of members as opposed to relying on subjective experience. This design process usually gives multiple member sizes that can be utilized for design loads. However, the team consistently tried to choose the member size with the lowest nominal weight, causing a reduction in overall cost. Solar panels were added on the southern building and the south-facing side of the roof, which optimizes sunlight exposure in winter and summer months. The team also added a green roof on top of the walkway between buildings and decided to fill out a LEED rating checklist. The items that the team checked off are items that we believe MSU would have no trouble in implementing and allow for a gold LEED rating. As you can see, with the given recommendations from the HOCKLE design team, the new STEM educational facility has the possibility of having a total of 65 points without adding much of an upfront cost. These 65 points in turn will allow for a gold LEED rating. The building already receives 5 points for renewable energy production and carbon offset. Some simply implemented items that the team checked off was indoor water use reduction water metering, indoor air quality management, and thermal comfort. The total cost for the entire structure is $9,053,977.83. The cost was determined by adding all the variables that you see in the table together, in which the total cost of steel was determined by multiplying the total weight of steel needed for the structure by $4 per pound of steel. The subtotal of steel was compiled, and then 20% was added for the erection and fabrication costs, and an additional 10% was added for the material necessary for connections. The total cost of concrete was understood by first multiplying the total square footage of the concrete slabs for each floor by their 6-inch thickness, then by their unit weight. This total volume of concrete was then multiplied by its unit price of $140 per cubic yard to get its subtotal price. The subtotal price then added 20% for fluff factor and 20% for labor to get a total price. The design fee was determined based on the work done by the structural team per hour, and the engineering fee was based on the sub-cost for the entire structure.
Hi, I'm Josh Cole, and I'll be discussing the transportation portion of this presentation. The overall goals for the transportation portion were to convert North Shaw Lane to pedestrian use only, and then divert all vehicular traffic to South Shaw Lane, all while keeping in mind sustainable practices. The regulations followed for this part of the project were derived from the American Association of State Highway and Transportation Officials. Basically, the main regulations we were following were regarding lane width and turning radius for city buses. So the main goals for this project were to maintain a high level of service for the intersections, account for the growth over the next 20 years and increase in traffic, and to also keep in mind sustainable practices for this design. So our current recommendation is to remove the bike lane from South Shaw Lane and then bump the roadway out to the north 1 lane, and then convert North Shaw Lane entirely to pedestrians and bicycle traffic only. There'll be some minor modifications made to the north side of the Red Cedar intersection of North Shaw, and then the intersection of North Shaw and Red Cedar will be converted to a pedestrian crossing. Here's the original site. The scope of our project extends east to just past Lot 40, and then to the west, just after West Shaw splits into North and South Shaw Lane, and then just north and south of each of the respective intersections. So here's our proposed site. Basically, it does everything that we were talking about. Pedestrians are kept to North Shaw, and then all the traffic is diverted to South Shaw. I'll be breaking this up into 4 different parts to make it a little easier to digest. So here's the North Shaw portion of the design. In the top figure, it's the North Shaw Lane and Red Cedar Road intersection. It's designed for pedestrians to have their own phase to allow them all to cross safely, and then you just have the through traffic on Red Cedar. There's no right or left turns. The bottom figure lays out the design for the length of the road, and the idea is to keep it the exact same width, so there won't be really any new pavement going in, but it will be redistributed. So we'll have 2 bike lanes at 6 foot 5 inches each, and then a single lane for foot traffic that's going to be 13 feet 4 inches. And then you have pedestrian and bicycle entrances and exits into lot 39 and 40 there. To the west side of the site, we have the area where we're going to be redirecting all traffic from West Shaw down onto South Shaw. So you can see kind of where there's that sidewalk entrance. That's a pre-existing sidewalk entrance that will take people off of North Shaw and onto the sidewalk. And then there's going to be a concrete barrier that will protect pedestrians and bicycle traffic from the vehicle traffic on West Shaw. And these lanes are all going to be their pre-existing width, which is 10 feet. Here's the figures for South Shaw Lane. The top figure is the South Shaw Lane Red Cedar Road intersection. The Red Cedar Road portion hasn't really changed much. The only difference is now the traffic has the ability to turn left or right at this intersection. However, the South Shaw and West Shaw Road portion that has changed a fair amount. Now the West Shaw portion will be 4 lanes, and the South Shaw portion will be 3 lanes with 1 storage lane for right turn or through movements. This was designed by basically inputting all projected traffic volume data into traffic simulation software and then figuring out which intersection is going to provide us with the highest level of service without increasing costs too much. And the bottom figure shows the entire length of the road. It'll be a 3-lane road where the northern 2 lanes are going to be westbound, and then the southernmost lane will be eastbound. Once you get near the parking lots, we're going to have a left turn lane in order to allow through traffic to proceed through uninterrupted, and traffic going into the parking lots will be able to turn safely. Additionally, we'll be adding a bus stop to the south side of Lot 40. So here are the modifications made to lots 39 and 40. Lot 39 is the top figure. From the original site, we're losing around 40 parking spaces. On both lots, the entrance and exits are modified. Exit is a right turn only in order to increase safety by decreasing the amount of turns across oncoming traffic. In Lot 40, we're losing about 30 parking spaces, and all these lost spaces are because of the expansion of South Shaw Lane about 11 feet north. So we had to cut some of the spaces out in order to create a buffer between the parking lot and the road. And the hope is that the decrease in parking spots will encourage people to either ride the bus or walk or ride their bikes, which will improve sustainability. So the overall cost for this portion of the project is going to run us to around 1.7, 1.8 million, and that was calculated using the MDOT weighted average item price report for 2019. Now, this includes only the materials. It doesn't include any of the labor or really anything beyond the price for the material, such as paints or signages or traffic signals. So that concludes the transportation design.
The recommended pavement structure for North Shaw Lane is a mill and fill overlay flexible pavement, which is essentially shaving 2 inches off the original flexible pavement and then overlaying on top of a fresh new 3 inches of hot mix asphalt. The 8-inch aggregate base is to remain there as well as the aggregate subbase of 12 inches. The roads and sidewalks of Northern Shaw Lane are to remain 12 inches, and for the parking lot and lanes around parking lot 39 and 40 are to become 10 feet for easier traffic flow. The bike lanes in this area are to remain 5 feet as well. The pavement grade is to be 0.5%. The main body of government responsible for controlling pavement designs and roadways is the Michigan Department of Transportation. Typically, they decide what is and what isn't allowed at a state level for pavements. Usually a pavement has a design life of about 20 years, and typically anything lower than that is usually frowned upon due to low materials expended using during that time. The material must also not have any unacceptable substances, i.e. no easily removed carcinogenic materials such as asbestos. You also need specialized permits when working on roadways construction, such as a utility and private road construction permit, a right-of-way construction permit, or an individual application and permit. Usually these are all accessible through MDOT. The design of the pavement also coincides with several different constraints or factors regarding their design. This is typically such as the width of the pavement, which is basically a given in a given area. If you give it in a given area, which is either between being 10 feet or 13 feet, or if we are just redoing a already present lane, you cannot change the width without severe alterations to the surroundings. And also, the constraint is the material used, which is either a flexible pavement, which is usually asphalt, hot mix asphalt over an aggregate base, or a concrete road, which is basically a highway style concrete slabs are connected together using rebar, and which are laid over a larger aggregate base. And also, of course, proximity to surrounding buildings and structures such as sidewalks, buildings, traffic lights, or utilities areas. In order to facilitate the designing of pavement structures, data must be gathered regarding the surroundings. This includes, but is not limited to, precipitation data, how much snowfall every year, how much rainfall, how frequently weather changes, how intense either storms are. We also need to collect local climate data regarding the location of pavements in order to create a pavement that doesn't react violently with the weather, and also might be able to such as frost depth, heat waves, so the asphalt doesn't melt. We also need to take several soil borings of the surroundings to see if the local subgrade soil is able to withstand vehicle weights moving over it, and so not to cause the pavement to sink beneath it. We need also federal and state guidelines need to be reviewed in order to find proper legality of pavement creation. Traffic demand and volume also need to be cited to be able to try to figure out how many ESALs, or equivalent single axle loads, are traveling over a given road every day. We also need to figure out its drainage requirements as allow water to flow downward and away from the pavement structure, as to not cause significant damage. The two pavements depicted here are a entirely new flexible pavement and an entirely new rigid pavement. Unfortunately, these two were not in my final decision because, due to the factor of being brand new, it means we had to replace all of the materials within these pavements down to the subgrade. But this is typically a very expensive procedure to do. So, and also due to the fact that our theme of East Shaw Hall Power Plant is sustainability, typically we would like to use less material, but having still an effective solution. These two designs here are the least material expensive because they are reusing the material already present within the pavement. The plan here both these plans are to overlay the old existing pavement with a new layer of hot mix asphalt to cover over / suppress any apparent deficiencies or problems located within the pavement layer. The first plan is to overlay the top pavement with a thick coat of HMA without modifying the existing pavement beneath it. The mill and fill flexible pavement plan is to shave approximately 2 inches off of the existing hot mix asphalt layer to remove any cracks or deficiencies within the pavement. Next, we would add a slightly smaller layer on top of the shaved layer in order to use less material while still maintaining a supportive structure. With this, the mill and fill flexible pavement is technically the less cost-effective method and is thus the correct answer material-wise. With the LCCAs finally finished, a proper decision can be made regarding total cost analysis of the pavements. As you can see in this photo, alternatives 1 and 2 are mostly more costly than alternatives 3 and 4 since they're entirely new material, and we are basically ripping out the old one, installing a completely new road in. Alternatives 3 and 4, however, reuse older materials, so are kind of less costly. Alternative 4 holds the lowest value for overall cost due to using the least amount of material, which is because instead of a full overlay, we're actually shaving a bit of the old asphalt away to make sure to make it use of it still use of it. Once we figured out the total material cost or capital cost of pavement design, we need to put it through a life cycle cost analysis. A life cycle cost analysis is essentially a method of acquiring, owning, and disposing of a building structure or system, which is basically taking into account the initial cost combined with any other costs associated with that building, such as maintenance, labor hired, traffic pushed away, future use costs, follow-up rehabilitation. Also, noticeably, at the end, of its life cycle, we get a small percentage of that money back by selling off the material as scrap, since we no longer are using that material. The main 3 outputs of a LCCA are the total cost, which is essentially basically the overall cost of all the materials, all the labor, all the maintenance, and any other costs that might be associated with this structure. Its present worth, which is essentially how much this road or structure is going to be worth in the next after 20 years. And then there is a equivalent unit annual cost, which is essentially the yearly modified cost that you are currently paying out for it over the next set of years.
The HOCKLE team has determined that the project will cost approximately $10.5 million. We can see the cost breakdown by discipline on this slide, with other costs taking up the majority of the fees. This is because we take into account soil erosion and sedimentation control, fees for permits. We'll also need traffic devices and traffic control while Shaw Lane is being reconstructed. We'll need pavement cleanup and overall project cleanup and mobilization. We'll also need water treatment operating costs In addition to asbestos remediation, there's significant asbestos in the Shaw Lane power plant that will need to be removed. Here we can see the project schedule. It takes place over approximately a year and a half with a 2 to 3 month buffer due to the impacts we predict due to the COVID-19 pandemic. In the first phase, we would like to internally demolish the Shaw Lane power plant and work on asbestos remediation. Next, during the spring, we would like to close off North Shaw Lane and begin the reconstructions of the lanes of South Shaw. We would also work on the expansion of parking lots. In that following summer, during March to June 2021, we would continue roadway construction and begin construction of the stormwater management system. We would start from the west end because on the east end would be the academic building, and we need to excavate and lay the foundation for that before we start to incorporate the stormwater system. We would also start to lay the rain gardens and place the underground storage tank. Following, and also occurring simultaneously in Phase D, we would open hole the area for the expansion of the academic building, lay the foundation, and establish the steel beams. In July and September of the same year, we would start to construct the external portions of the building, complete the stormwater system, and develop the green roof. Later that fall, we would like to complete the road work and develop the internal components of the building, like room divisions, electrical, gas, and water distribution piping. Last, when we return from the holiday vacation, we don't include any time working in December. We would like to complete anything that remains in the academic building as far as internal utilities. The HOCKLE team recognizes that this project will have significant impacts on the MSU community. This will become one of the most highly trafficked areas on campus due to the increase of classroom space, and it will become a central hub for the campus community. It will definitely provide resources for students to engage in learning, professors opportunities to engage in more advanced research, and opportunities for the university to attract new talent. We had a pleasure working on this project.